Assalamualaikum and a very good day to our lecturer and classmates. My name is Ahmad Temizi bin Ahmad Zaimuri, EL22025. Today, we will be presenting our assignment submission on the design, modeling and performance analysis of a closed-loop variable frequency drive system using MATLAB Simulink. The core objective of this simulation is to analyze how a three-phase voltage source inverter regulates the speed and electromagnetic torque of an AC machine under a fixed mechanical load. Let's start by breaking down the circuit topology and the control strategy that we were implemented.
Hello, my name is Muhammad Farid Farhan bin Marahi, and I will resume from the others of the presentations. As we can see here is in the power stage, the system is managed by the constant DC voltage source. This DC line feed three-phase 6-switch inverter bridge using IGBT, or should we say diode pair that labels S1 through S6. The inverter role is to synthesize a balanced three-phase the AC voltage to drive our AC machines. To ensure precise speed tracking, I designed a closed-loop control. We designed actually closed-loop control systems that on the picture right now that been shows. First, the actual rotor speed is fed back and subtract from our target reference speeds, which is set to 1500 RPM. As you can see, the resulting error signal is processing by the discrete IP controller to minimize standby stage error, and the control output is then integrate into electrical angle reference based on 50 Hz rated frequency configurations. Finally, we use sinusoidal pulse wave modulations, that short SPWMs. The three generation sine wave reference compares against a high frequencies triangle carrier wave. This generate the precise getting signals, that is S1 to S6 needed to command our inverter switch. Now let's look at the performance waveforms over 10-second simulation runs. Looking at the speed feedback score, we can see as increased stable response after a minor frequency of the second transmission overshoots at the startup. The line set up perfectly flat at our scale target value. It proved that the tuned IP control successfully eliminates standby stage tracking error. Now let's look at the inverter output currents. At exactly time t, that is time equal to 0 seconds, there is an unexpected transmits in rush current spike, peaking around plus minus 140 ampere. This happened as a motor developed inertial magnetic flux and overcome rotor initiate within less than 0.25 seconds. The transients clear, setting into the beautiful balance, controlling three-phase sinusoidal bands of plus minus 500 amperes. This brings us to motor dynamic. In the simulations, a constant mechanical loop torque, that is TMs, of negative 100 Newton meters is applied to the machines. On top axis, the electromagnetic torque undergo an initial startup oscillations matching our inrush currents. However, it rapidly stabilizes exactly at the negative 100 Newton meters. This perfectly balanced confirms that the motor has achieved dynamic equilibrium with the load. On the top axis, the rotor angle shows a flawless unified sawtooth frames because the speed is perfectly constant. The angle initiates lightly from 0 to 2 pi radians repeatedly without any distortions. That's all for me.
Assalamualaikum. My name is Muhammad Fakri bin Zaid Kamaruddin. I am from Group 8. My ID number is EL22023. I will talk about DC to DC converter simulation using MATLAB Simulink. The circuit start with the DC voltage source connected to inductor, MOSFET, diode and capacitor. For being a boost converter, the converter increases the input voltage and supply it to the DC motor. I use PWM generator and a PID controller to regulate the duty cycle, ensuring smooth voltage control and stable motor speed. The measurement include voltage, current, torque, and speed, which are displayed and monitored through the scope block. From the simulation result, you can see the motor speed rise quickly and stabilize around 418 radian per second, while the armature current settle near 2.6 ampere and torque around 2.5 Nm. This shows the converter and controller system work effectively to maintain steady performance. Overall, this model demonstrates how DC to DC converter can efficiently control a DC motor using PWM and PID feedback.
In conclusion, this project successfully demonstrates the design and simulation of a closed-loop motor drive system using power electronic converters and feedback control techniques. For the DC motor system, the boost converter effectively increased the input voltage and together with the PWM and PID controller maintained a stable motor speed, current and torque response. The simulation results shown fast settling time and reliable steady-state performance. For the AC motor drive system, the three-phase converter combined with SPWM switching and PI system speed control successfully regulated the motor speed to the desired reference value. The system exhibits minimal steady-state error, stable current waveforms, and balanced electromagnetic torque under load conditions. Overall, the simulation result confirm the proposed control strategies provide efficient motor operation, accurate speed regulation, and stable dynamic performance. This finding demonstrate the importance of power electronic converters and closed-loop controllers in modern motor drive application used in industrial automation and electric transportation system. Thank you for your attention, and that's all from our group.